Hi, everyone. My name is John. I'm giving this talk on, it's titled Securing Protocols with Not So Formal Methods. So the idea here is to present a particular approach to looking at and thinking about protocols, whether you are, building a protocol for some purpose, or maybe you are trying to find flaws in an existing protocol, because protocols are everywhere. So a bit about me. I'm currently working as a security research engineer at Hewlett-Packard. I did my master's in information security and chronic procrastination. And I was, for that, I received an award. Doing pretty all right, I think. So formal methods, what exactly are they? Simply, we use them to analyze programs or systems using maths. Please don't leave. But actually, there's going to be very little maths. Actually, no maths in this talk, so you're all safe. But actually, formal methods are pretty cool because they are what give us confidence in our cryptographic primitives. That the algorithms we use are secure. So, what do I mean by primitives? These are your sort of standard cryptographic algorithms, things like AES, RSA, SHA-256, etc. And we call them primitives simply, of course, because they're not terribly useful on their own. We use them to construct bigger systems, for example, protocols. So you may have heard that designing cryptographic primitives correctly, it's kind of hard. Good news. Using these primitives correctly is super easy. It's a total walk in the park. Oh no, wait, that's completely wrong. So luckily for us, we can apply formal methods to things like protocols also, and many people have. But first, just to be clear, what do we mean by protocol? So for the purposes of this talk today, we're going to say that a protocol is simply a defined way of communicating between devices in service of some goal, right? And on the slide, we have an example of a pretty bad authentication protocol. But using formal methods, we could take this protocol and prove that it is secure, or maybe that it's not so secure as we might have thought. And we have proofs for many different protocols, TLS, Kerberos, even secure messaging apps like Signal and Matrix. People have analyzed those protocols and found flaws in them. OAuth is another one. So if we look at formal verification for security, this is roughly how it works, okay? So we have a system, and that, in our case, we're talking about a protocol. It could also be a program, perhaps, that we're looking at. And this system will have different elements, right? Different parties, different algorithm subroutines, or, if we're talking about protocols, individual messages, right? And we can take these elements and model them using mathematical constructs, right? So we translate, something in the real world into some, conceptual model, basically. And we write all of this down in excruciating detail. So then we take our model that we've written out, and we write, based on that model, a set of security definitions. So what does it mean for something to be secure? That's a quite open-ended question, and it's going to depend on your particular use case. Is confidentiality important for you? How about non-repudiation? Maybe you're looking for forward secrecy. Well, you need to capture those in formal definitions. And then finally, you produce a set of proofs based on proving those security definitions in the context of your model, right? Just to clarify, though, I have a picture of dice on the screen there. I'm not suggesting that you should take dice and, do a roll of the dice to figure out whether your protocol is secure or not. I'm actually referencing a particular type of proof there called a game-based proof, but that's neither here or there. There is a problem, though, unfortunately, with formal verification. So recently, I used formal methods in a research paper, which I'm still working on, actually. So here are the pages that give the model and the proofs. But okay, that's a lot, but we're done. Oh no, wait, I lied. There's more. So it's a lot. But at least at the end of it, we have fairly good assurance that this protocol that's been analyzed is secure. But that's about 18 pages, give or take. And there are ways in which there are methods of doing this which don't require you to do it by hand, like I've done there. But it's still, very time consuming. It's a lot of work. In summary, if we look at formal methods or formal verification, we can kind of look at it as like a function that, takes as arguments a protocol, blood, sweat, and tears, and returns either a proof of security or, failing that, gives you a flaw in the protocol. Now, I have a theory, and that's that you can take this and modify it slightly, that you can simplify things and get rid of the blood, sweat, and tears that goes into formal analysis. Now, if you do this, you're not going to get a full proof of security, but you can get some general assurance. And sometimes that's good enough, because you can still use this to find flaws in a protocol. So, in the remainder of this talk, I'm going to be talking about sort of lessons that we can learn from formal analysis. And hopefully, we can apply these lessons whenever we approach a protocol, not just when we need the rigor of formal proofs. So, to do this, we're going to work through a real-world example of a protocol together. All right, so I'm going to present to you a problem, or a given scenario, really. So we're going to be working with this open source project that is for, it does remote attestation and verification. So what does that mean? So remote attestation is a technique that allows a device to sort of report its state to another system, right? And then that other system will verify the state. So it will make a determination about whether the reported state is, first of all, an accurate representation of the system state, but also whether that state is sort of as is expected. And we'll talk a bit more about what that means in a second. So the project that I'm talking about is called Keylime, and it can be found at that URL. Okay, if we consider this system of ours, this remote attestation verification system, we have some device, right? And this can be a server, it could be a network switch, it could be, potentially a workstation, And this device could be in a secure data center, or maybe it's somewhere without good physical access control. Maybe it's in a retail environment, right? So anyone can maybe walk up to that device, plug something in, maybe swap out a PCI card for a different PCI card, maybe change the boot order of the system, install software that is not authorized, etc. So we want to be able to detect if that happens. So this device of ours, it contains inside it a TPM. So if you don't know what a TPM is, it's basically a sort of a cryptographic processor. It does cryptographic operations, but more importantly, it has sort of secure storage, or storage that is supposed to be prevented from tampering. So if you store a key in the TPM, you're pretty sure that it's not going to leak, hopefully. And the TPM sort of receives sort of measures of system state, and we'll talk more about that in a second. Additionally, the device will have a software agent running on it, and this agent is what will gather the system state and report it to that central server. So speaking of central servers, we have two of them. We have a registrar, which simply keeps track of all our devices in our network or deployed in the field. And we have a verifier, and that's what actually receives the state and makes a determination of whether it verifies according to a given policy or not. So, at a high level, let's quickly think about our trust assumptions here. First of all, we obviously trust our TPM. Without our TPM, none of this works. So we trust that the TPM is built according to spec, and it's built by a trusted manufacturer and behaves as we expect it to. Similarly, we trust the registrar and the verifier, obviously, because, well, in the case of the verifier, we need to trust what it tells us about the state of that device. But we don't actually trust the agent or the device itself, or perhaps a more accurate way of putting this is that we might trust these devices conditionally. So once, if the verifier says that the state is as we expect, then we might trust that device. And that is exactly what happens in workload authentication. If anyone is familiar with SPIFFE or Spire, that's exactly what happens. SPIFFE or Spire will issue a credential to a device, but conditionally based on whether or not that attestation has verified successfully. All right, so to achieve all this, we have sort of different phases that take place. We have, first of all, a registration protocol. At a high level, how this works is that the agent, when it starts up for the first time, it will retrieve something called an EK, or an endorsement key, from the TPM, and also a EK cert, and that's just the X509 certificate, which contains the public portion of the EK, and it is signed by the manufacturer of the TPM. All right. And then we also get a attestation key, or we request a new attestation key be created, and we retrieve that. So the agent receives these keys, and it reports these to the registrar. Now, when the registrar receives them, it checks to make sure that certificate is issued by a trusted TPM manufacturer. It also will check to make sure that the EK and the AK it receives are both resident in the same TPM. And there's a specific mechanism defined in the TPM spec by which you do that. All right, so that's registration. Now, for the actual attestation, when the device reports its state to the verifier, how does that work? So, first of all, periodically, various logs from the device will get sort of read, in a sense, by the TPM. But the TPM doesn't store the logs because it doesn't have the capacity to do so. It simply stores a hash of those logs. And by the way, if I'm talking about logs here, these can be things like UEFI logs, which will contain your PCI devices that could connected the version of the firmware that's running, etc. There's various things that it could be. There's also IMA, which is a Linux technology which reports on what files are the contents of files when they are sort of read into memory. So these logs can be various measures of system state. But the TPM basically stores a hash of those logs. So the verifier will periodically request an attestation from the agent. And the agent will then request what is called a TPM quote from the TPM. And this is a rough hand-wavy approximation here because the details aren't super important to us. But basically the TPM will certify that, it has this particular hash, which again is a hash of our logs, in its registers somewhere, right? And it sort of provides that quote to the agent, which the agent, of course, the agent receives the quote and combines this with the actual logs. So it has effectively a hash of the logs and the logs themselves, and then it reports both of those things together to the verifier. And that hash is sort of signed by the TPM, if you would. So now that we understand roughly how this whole system works, let's build a model together. All right, so we're going to do this very sort of back of the napkin approach. We're not going to do it according to the painstaking process of that you usually would when you're doing a formal model. And we're not going to use precise mathematical terms. And our focus is going to be on what the attacker can actually accomplish. This is what is known as an adversarial model. All right, so very quickly, we have parties, a verifier, a registrar, a tenant. Forget about the tenant. We have a verifier and a registrar. And we have sort of many different nodes or attested devices, right? Each node has a TPM and an agent, as we discussed before, and you can view these as parties themselves, right? Because again, the TPM has different trust assumptions from our agent, even though they form part of the same node. And each node also has a representation of its state, which will sort of abstract away as sort of a particular value. We don't really care what the value is. You can think of it like a JSON file, maybe, if you wanted to, that has, say, your PCI cards in it or whatever. And then each TPM contains a hash of its node's state value. And so you'll notice here that we're not being very precise. We're sort of approximating things. And that's sort of how you would do a formal model as well. That's how formal modeling works as well. Is that, you don't get every detail. You just get, you get a close enough approximation. So we also have some keys. Our registrar, our verifier and our registrar both have a TLS certificate, and they're both issued by the same certificate authority. And they possess the private key, obviously, and they all trust that CA. And the agents in our system also trust the CA. The CA is sort of preloaded in the agents. And we have, our TPM has that EK and AK that we talked about previously. So policies. Now, our verifier keeps a mapping of nodes to policies. So a policy simply describes what the node's state value is sort of expected to contain. And you can think of this as sort of like an authentication policy or authorization policy, I should say. So you have a set of rules about what you expect to see in that state value. All right. So now we're going to talk about our adversary. Here we have what is known as a network-based attacker. So the attacker controls the network, and it is the network. So it means it can intercept, it can block, it can modify any messages which traverse the network. And that's quite standard. We have these network-based attackers in most protocol analysis we'll have this. But we're also going to add some additional capabilities to the adversary. So the adversary may additionally corrupt a node at its discretion. So this means that it can access or modify any and all data stored by the agent, including any private keys, access and modifies the node state value, intercept the agent's reading of the state value, and exercise full control over the channel between the TPM and the agent. So why are we doing this? Right? Because we are trying to detect modifications of that end system. So we have to allow attacks in which the attacker is resident on that attested system, right? So that's why we're doing this. All right. But notably, the adversary cannot corrupt a TPM, and it cannot break any cryptographic primitives. All right. So now our security definition. Often it's useful to think, what's the purpose of this particular protocol that we're looking at? So in this case, we're trying to get this verification result at the end of the day. Either yes or no. It matches policy, it doesn't match policy. And we want that result to actually reflect the state of the device, right? So we'll call our security property verification security. So a successful attack against verification security we'll say that it's when there's a mismatch between two things. A verification outcome as determined by the verifier and the correct expected verification outcome for that particular node. So this means that an attack in which verification passes when it shouldn't pass is a valid attack, and the inverse of that is also a valid attack. But attacks which exploit poorly defined verification policies, so your policy doesn't, capture that particular modification of the system, that's out of scope. Also, these measures of system state are just measures. They're not a complete picture of the system state, right? So attacks which involve modifying those parts which aren't reported to the verifier are also, of course, out of scope. All right. So now, using this, let's actually look at some protocols together. So here's an example registration protocol for Keylime. In fact, this is the current registration protocol that exists today. So we have three parties, RTPM, an agent, and a registrar, or the registrar. And notably, this protocol doesn't use TLS at all. It's all in clear text. All right, so our agent sends that EK pub, that EK cert, and the AK pub, as previously discussed, to the registrar. And the registrar verifies that cert against the TPM manufacturer certificate. And if that passes, it generates a new random key, which we'll call K. And now the registrar is going to use that K value to check if there's a binding between the AK and the EK. So the way it does this, roughly speaking, this is not actually how it works in practice. I am simplifying things. But basically, the registrar encrypts, first of all, it concatenates the AK with that random K value, and it encrypts the result of that with the EK pub. And the agent just forwards that to the TPM. Now, and this is a defined process in the TPM spec again. So the TPM will decrypt the EK, will decrypt that package that it's received using the EK or the private portion of the EK, right? And then it's going to check to see if that AK that's contained within it, if it's the owner of that AK. If it has that AK stored in its registers. And if so, only if that check passes does it release the K value to the agent. Then the agent performs a HMAC of its ID using that K as the key and sends that to the registrar. And now the registrar can be certain that that AK and EK are resident within the same TPM. Okay? But there are some issues here. So let's sort of think of some of the things that the adversary can do. So what if the adversary steals the EK and the AK? Remember that all of this is in clear text and the adversary has full control over the network. So it can pull out that EK pub, that certificate, that AK pub, right? And this is in a run between agent 1, TPM 1, right? Okay, so the confidentiality of these keys aren't protected, right? But now, so it takes those and injects them into a different run of the protocol. So now we have a registration protocol happening with a different agent 2, and a different TPM 2, right? So instead, it swaps in those that EK and the AK from the previous run, because again, it can do that. And then as a result of that, the sort of value that the registrar sends back is actually encrypted with the other agent's EK pub, and it contains the other agent's AK. And now we don't want that message to go through, because if this TPM receives that, it's not going to be able to do anything with that. That would be pointless. So we just go ahead and block that request. But the adversary saves that for future. So if we return now to our first run of the protocol, we can take that encrypted message from the other run and inject it here in place of the encrypted message that the registrar sends back. So the registrar sends back that encrypted message, and our adversary swaps it out for the other encrypted message. And that always obviously carries all the way through. The agent forwards that to the TPM. But actually, note now that this EK pub is the EK pub for this TPM1, right? Because we swapped it in the other run of the protocol. So this TPM decrypts K prime, which is the K that from the other run of the protocol, successfully. Now, because of our adversary's additional capabilities, remember we've said that the adversary can corrupt an agent, right? So we can actually retrieve that K prime from the agent's memory. And now, if we return to our second run of the protocol, we don't even have to do the rest of this protocol, in fact, right? Because we have knowledge of that K prime now. So using that knowledge of the K prime, we can just do this HMAC ourselves as the adversary, right? And now, as a result of this, we have the registrar associating the wrong TPM, or is associating a TPM with the wrong agent, if that makes sense. So agent 1's TPM is associated with agent 2 effectively. So that breaks, of course, our security property, right? Because that could cause verification to fail. Because it's expecting it for one system, or the verifier is expecting state from one system and it's actually getting state from another system. Now, I've run out of time here. There are more attacks that can be done against this protocol. And we've looked at them, by upgrading the protocol with TLS on the registrar side, so server authenticated TLS. Turns out even if you do that still doesn't fix the issue. We also tried to fix the issue by implementing mutual TLS between the agent and the registrar. But that also doesn't fix the issue because, again, the adversary can read the file system of the node. So even though there's mutual authentication, it can retrieve that private key from the agent, and so it can still sort of impersonate the agent. So yeah, here's the example with mutually authenticated TLS. And again, our adversary can take control of that agent and impersonate it going forward. So suffice to say that this protocol is quite broken. Now, I wish I had more time to go into this more. I've been working with these keyline protocols for the last, 6 months or so. And it's not just the registration protocol, it sort of goes beyond that. And we're working on fixing this actually. There is a proposal that I've written, to sort of redesign these protocols, that the community is working on. So good news there. So quick summary. By sort of doing this sort of informal protocol analysis, we've actually managed to discover attacks on these protocols. We have 2 attacks, in fact. We didn't get into attack 2 really. But both of these attacks result in a verification policy being applied to the wrong node. And so we achieve this by sort of very coarsely modeling our system, outlining the attacker's capabilities, and defining certain security properties. So I would encourage you that next time you're looking at a sequence diagram for some protocol, that you try and think in terms of the adversary. Who is our adversary? What can they actually do? Because if you do that, then you are sort of developing this mindset which helps you to identify weaknesses, and helps you to think through the implications of your design decisions. So that's it. That's my talk. Anybody have any questions? Yes.
I have a question. So it looks like we are trusting VPNs and not devices.
Correct.
This is advice, right? So I cannot store a VPN because you are verifying the manufacturer of that VPN.
Right.
So I'm not very familiar with how VPNs work, but is there any way that besides verifying the manufacturer of the VPN, I can have sort of personalization of my VPNs? Because let's say that we use brand A, and you have physical access to my device, you need to swap the VPN, and it's yours because it will pass the manufacturer verification. But what happens if I have a VPN signed with an exclusive key or identifier for my company? Even if you swap the VPN, you need to swap my key material or whatever, personally, my own VPN. So it's just an idea, but I don't know if that somehow mitigates the threat of physical access and spoofing VPNs.
Well, so interestingly, you're not supposed to be able to swap TPMs. They're sort of soldered onto the motherboard typically. But, you can sort of in effect. And that's kind of what we do in one of these attacks. basically the attacker in this attack, has its own TPM, right? And it uses that TPM to do bad things. Because you're right, we're just trusting any TPM, right? Because a TPM doesn't identify a device, in fact. In fact, the spec expressly says that it's not supposed to do that. So if you're using a TPM for purposes of identifying a device, authenticating a particular device, then that's not an appropriate use case. And this is, I think, the trap that the keyline people sort of fell into, is thinking that, we have these keys, we have these certificates, we have authentication. We don't actually have authentication of that device, in effect. Does that make sense? Does that sort of answer your question?
There are standards, there's a WebID standard, a call cert standard, but the manufacturer is divided into two.
Yes. That's a very good point. Yeah. Actually, one of our proposed fixes is through the use of dev IDs. And, Yeah, then you bind the TPM to a particular device with a particular serial number. And that. Any other questions? All right. Well, thanks so much. Thanks for your patience, everyone.